So in the last lesson, when we introduced the idea of logarithms, we talked a lot about how it's a brand new language and it takes a lot of getting used to at first, but if you do the practice and work through it and those two little tricks that I talked about, that are things to remember to keep on top of your mind when you're doing this work, then by the time we get to the end of the unit, you should be thinking in logarithms and just understanding them and being able to evaluate them. So, we're going to hopefully get deeper into that today with the lessons that we're doing. And we're going to look at this lesson, and the next one is all about a few logarithmic properties, some of which, a couple in particular, are really, really big deals, really important properties that we're going to need to know. And then we're going to use those properties and just understanding of logarithms to evaluate some more logarithmic expressions and get into solving some more complicated equations, which is what logarithms will eventually be very useful for, you'll see. Okay, so that's what we're doing in the first lesson here. And the second lesson is going to be kind of more of the same. We'll add a couple of extra little things, but it'll be more working with the properties. So 2 days on properties of logarithms. So we'll start with just a reminder of what a logarithm is. And I said this on Friday, and because it's their first time seeing them, it may not have sunk in, but hopefully you've been working with them now and you're kind of getting it. And I'll say this again. If you get to the test and you have that moment of panic and where you're like, oh my gosh, what is a logarithm? Well, what you want to do, so we're going to rewrite this. Okay, I'll rewrite it first and then I'll finish that statement. So you should be able to rewrite it, but if you can't. So it's 2 to the x. Remember, the base stays the same. Base stays the same. That's, whoops, my microphone fell. That's one of my 2 reminders, like things to keep on top of your mind whenever you're working with logarithms, when you're first learning them, or those of you that are taking calculus, this is going to be interesting. Both calculus sections are in the 4th quadrimester. So you're taking this now, and then you're basically going to have whatever it is, 6 or more months off of this kind of math before you have to take or get to take calculus. And we do logarithms at the end of calculus. So it's going to be like a long time, which is, generally speaking, a terrible idea. That's why it's really nice if you take this course and then calculus in the same year back to back when it's fresh in your mind. Anyway, when you go to calculus, you're going to have to remind yourself a little bit of what logarithms are because you won't have seen them in so long. You'll be like, wait a minute, how do these things work again? And you'll just kind of have to warm yourself back up. And these 2 tricks are what you want to think of, right? The base stays the same. Of course, that means you have to know where the base is in the logarithm, but that's your base. So that's still the base when you write it as a power. Base stays the same, and logarithms calculate or find exponents. So that means if the result of evaluating a logarithm is an exponent, x has to be the exponent, right? That's what that means. So 2 to the x equals 8. So what is x going to be? 3. So like if you're trying to figure this out because you have that moment of panic on a test, do that. 2 to the 3 equals 8. Okay, now how do I write this as a logarithm? And if you write it wrong, if you write like log base 8 of 2 equals 3 or something like that, if you have this button, if you don't, you can still do this. That's coming up in the next lesson, I believe, where I'll show you how to use the other button on your calculator to do all kinds of logs. But I could type it in, log base 8 of 2, and it should give me 3. Oh, it didn't. It gave me 1/3, but it didn't give me 3. So I have written it wrong, right? And so then go back and fix it. Log base 2 of 8 equals 3. So log base 2 of 8 is 3. So this is the correct way to write them, and use that as your model for the rest of the test. Okay? That would be my recommendation of something to keep in mind, something to use, I guess, if you have that moment of panic. Okay, but that's just our quick reminder of the relationship between a logarithm and an exponential function or a power and how they're related. And so what we are going to do is we are going to explore some properties, and we are going to rewrite these in exponential form in order to explore them. It's going to be a little bit weird what we do, so I hope you're able to follow it. Okay. In the end, you just need to know the properties. Okay. And there's two kind of super important ones. One that we sort of already saw. I just didn't really point out that it was a property, but we were using it in the last lesson. But another one that's really important. And if you know those two, you can kind of figure out all the rest anyway. Okay, so keep that in mind. But to the point of the question that was asked earlier, like, can't I just say let this equal x and rewrite it and solve that? I mean, you can, and that's kind of what we're going to do. But ultimately, our goal is to learn what is true about logarithms. So if I have a logarithm, I can just evaluate it in itself and not turn it into exponent. I mean, the thing is, eventually we're going to be solving exponential equations using logarithms. If our only way of evaluating a logarithm is by converting it back to an exponential equation, kind of defeats the purpose, right? So we do want to get comfortable with these things. So here's what I'm going to do, and I'm going to do this in green because this is just showing my thinking. This is how I'm, like what's the answer to this? This is what we're trying to figure out. And we're going to use exponential equations because we're more comfortable with them to do it. But what we ultimately want to know is, what is this equal to? What's this property? And the property that we're talking about is hopefully, obviously, when the base of the log and the argument of the log are the same, right? Log base a of a, what is it? So remember, this is asking, this is my question mark. Logs calculate exponents. The base stays the same, so there's my base. This a is going here of something equals a. So what is that something? Ben, 1. Good. So 1. So that means the answer to this is 1. Log base a of a. If the argument is the same as the base, the result is 1. Again, you could punch this into your calculator. Log. In fact, we could do it with our this button that's log base 10. Log of 10 should give me 1. Right? Okay, good. Some of these are going to come up more often than others. Like I don't know that this one's going to come up very often, but that's fine. So a to the something equals 1. What is that something? Yeah? 0. A to the 0 is 1. That means log base a of 1 must equal 0. Again, you can go ahead and check that on your calculator. Pick any base you want. Log base 10 of 1, and you should get 0. Otherwise, your calculator is broken. Log base a of a to the x. So again, the base is the same as the base in the argument, but the argument also has an exponent. So the argument, which is what I'm taking the logarithm of, okay, is a to the x. That whole thing is the argument. And like some people might think that it looks like this, log base a of a all to the x. That's not what this means. And that can be ambiguous a little bit, and sometimes with logarithms we have to be very careful how we use brackets in order to be clear what we mean by exponents. But anyway, log base a of a to the x. So the base of the logarithm is the same as the base in the argument. And so how do I rewrite this? A to the something, because again, I'm looking for that exponent, right? That's what logarithms do, equals. If you were to recreate this, which I'm not going to put any of this on a test, so you're not going to have to do that. But if you were to recreate this, all of this is based on this. If I can rewrite this like that, then when it starts to become variables, a's and x's, it gets a little bit fuzzier what goes where, but you just have to sort of slow yourself down and focus and realize that this a to the x has to go over there, right? Just like the 8 went over there when we rewrote the last one. So what's the answer? What exponent do I put on a so that it's equal to a to the x? X. Very good. Right? And it kind of seems like a silly question, or you like, is that really what this is asking for? Yeah, that's what it's asking for. But this is a big deal. This is one of the big properties that I was talking about. Log base a of a to the x equals x. And this is the one that we were actually using in the last day when we were evaluating these. And I showed you a little demonstration comparing it to solving exponential equations the way you do it in grade 11 to show you why the way we were doing it worked, but I didn't talk about it as a property. But it turns out this is a property. Log base, let's say 5 of 5 cubed is 3. Right? So again, your calculator can confirm all of these, and that might be another useful thing for you to be able to do on a test is confirm what the result is. If you've got x's and a's in there, you can't punch that in a calculator, but you could just make up your own numbers to figure it out. This one's kind of wonky. This one's harder. This one is written as an exponent. In exponential form as a power. So we're going to rewrite it in logarithmic form, and I think a lot of people have a hard time following how that logarithmic form works. This exponent has a base of a. Okay? So it's log base a of this thing, right? That becomes my argument. Equals the exponent. Because this is now a logarithm, and logarithms calculate exponents. Now my exponent happens to be a logarithm, but it could be anything. Okay? So log base a of x. This exponent went there. Now, what do I put in the box? X again. Good. Because log base a of x has to be log base a of x. So this is actually almost identical to this one, but we're going to use this one a lot, and we're going to use this one basically none at all. And so you'll get used to this one, and it's just easier to follow what's happening, and you won't get as used to this one. But it's the same thing. This is a logarithm with a base of a of a power with a base of a. Well, this is a power with a base of a, and the exponent has a logarithm with a base of a. So those are opposite operations. They're canceling each other out, and that's why you're left with just your x in both cases. Like I say, we don't see this one very much. It's in the worksheet a couple of times. It'll be on the review, and then there'll be one on the test for 1 mark. And you just want to remember that it's that funky case that looks weird, and so it's just this. The answer is just that. We'll do an example, and I'll talk about that again further into the lesson, but that's a tricky one. When you've got a log in the exponent, and you say, oh, it's that tricky kind. That's what I would try to think of. Okay? Yeah?
So is the variable, it's always just log and then whatever variable with it? Like a, b, or c? Like you just turned a into log a?
I rewrote this in logarithmic form. Right. This is the exponent. That goes over there. Yeah. 2 cubed equals 8. Log base 2 of 8, this thing, which is the x, which is here, equals 3. So the exponent goes over there. Base stays the same.
Yeah, I know that.
Yeah.
But like, how do you get the log? It's just log a from like just a?
This part right here?
Like the first part, yeah.
It's log base a of something.
Yeah.
Yeah, you can't just have log base a of nothing. You have to have an argument. Yeah. So you got to be taking the log of something. But that's the question we were asking. What are we taking the log of? right? That was our unknown. So I made it an empty box. I could have used brackets, I suppose. Log base A of something equals log base A of x. The something has to be an x. We're doing, this is what I'm saying. I don't want to spend too much more time on it. It's not super important. We're looking at these properties by doing some inspection on things. But it's always true that the rewriting of this one is a little bit harder to follow. You don't need to know how to prove it. You just need to know how to apply it. But if it's still bugging you and you want to talk about it more after, then we can do that. Okay. All right. Again, I'm not going to prove these, but we're going to do a little playing around to see if we can figure out what the relationship is. And I'm going to do this two ways, and that's what we're going to do. A lot of these things that we're going to do, you're going to notice we do them in a couple of different ways. So one of the really cool things about logarithms is there's often just subtle differences in how you might solve a problem, and it's different from how I might do it or somebody else in the class might do it. Okay, so I'm going to come over here and do one of them. And so this way I'm going to simplify inside the argument. Okay, so this is log. What's the base when there's no base written? Something you have to know, right? You can't get to the test and say, oh, what is it again? 10. So this is log base 10, so I'm writing it in for that clarity, but I'm not going to always do that. That's something we need to know. And what's the rule? Multiplying powers of the same base, you add the exponents. So it's 10 to the 5. And we just determine this property. So this result is 5, right? We get that? That now this is a property, a rule that we're going to use over and over and over again. Like I said, we were kind of using it. But now we really get to use it. So what we're going to explore is there some property that relates the logarithm of a product to be equal to the logarithm of the different parts of the product separately? Do you understand what I mean? So is there something, some operation that will become a property for us where I'm taking the log of a product, I can do the logs individually. So we can evaluate this. Is that true? So there's like an operation in there. Log base 10 of 10 squared is? Huh? No. We're not ready to do inside the box yet. We're not finished. It's 2, thank you. And this one, log base 10 of 10 cubed is 3. And we know that it has to equal 5 because of that, right? Because it equaled 5 over there, so this has to equal 5 as well. So this is the hard part. Don't shout it out. Does anybody know any mathematical operation that I could put between the 2 and the 3 so that it gives me 5? This is tricky. What? What's so funny? Do you know something? Addition. Oh, I didn't even think of that. Very good. Okay, so that's the property right there. The property is if I'm adding 2 logs with the same base, I could take the log of their product of the arguments of those 2 logs. Often we're going to actually kind of use this in reverse order, but we do use it a little bit both directions. And this is something that we will revisit. This is not a formal proof. It's pretty convincing. I think a lot of students find this more convincing than a formal proof. Because formal proofs are often just they use all variables and they're thicker and just harder to follow, right? But this is not a formal proof. But like I say, very convincing. And for us now, it's good enough to be used. So we'll do the same thing very quickly for division. log base 10 of 10 to the dividing powers of the same base, 9 minus 6, right? So log base 10 of 3, which is 3. Log base 10 of 10 to the 9, some unknown operation. Log base 10 of 10 to the 6. Log base 10 of 10 to the 9 is 9. Log base 10 of 10 to the 6 is 6. And we know it has to equal 3. So what's this mysterious mathematical operation that relates 9 and 6 and gives us 3? Again, it's obvious. Subtraction. So if you spend a bit of time thinking about these, I think it becomes obvious to see that this is just the same rules that we used here, where you're multiplying powers at the same base, you subtract the exponents. It's the same rule, same property, but written as logarithms, right? But it's directly related to that property in exponents. So division and subtraction become true, are related, and multiplication and addition are related. For some of you, you're going to like it a lot more when we do this with examples, with numbers. And that's fine. Okay, this is the last strange thing I'm going to do, and I'm going to qualify this again, that if you don't follow the next 5 minutes or so, don't worry about it. You don't need to be able to do what I'm about to do. You just need to know the property. But if anybody was going further, we do these, and in the normal years, we do more of them. We do a lot more proofs and derivations of things. And we're going to cut back on some of those just because, you know, it's been more challenging on you to learn all of it at once and then pay attention to those things. So we're cutting back on some of that stuff. But it's still useful to see some of these, the ways that you derive these properties, or the tricks that mathematicians use to prove properties or explore properties. I think it's useful to have seen it. And so if you don't fully understand it, that's okay. But if any of you take math or engineering or even some sciences, I'm sure, like physics in particular, but chemistry too, if you took that in university, you might start being required to do more of this kind of stuff. So even though we're not going to practice it a lot in high school, if you've seen it, that's something. You know what I mean? So we're going to do that. So first thing I'm going to do, but the thing about proofs or derivations or these kind of tricky things, this is not a proof as well, what I'm about to do, but it's close to one, is that a lot of students go, well, why would you know to do that? Well, you wouldn't until you've seen the proof and you kind of, I guess, memorize it. How did the first person know to do it? Well, they were just messing around with stuff and figured it out, right? So in order to explore this final property, and this final property is probably the most important one that we're going to see, I start with this and I rewrite it in exponential form. So this is 2 to the x equals 7, right? And then I'm going to move over to something else, log base 2 of 7 cubed. But this statement right here says 7 is equal to 2 to the x, right? If two things are equal, I can replace one with the other. So I can do this. This equals, I'll do it below. This equals log base 2 of 2 to the x, all cubed. Because all I've done is realize that based on this statement on this side, 2 to the x is equal to 7. So instead of the 7 in here, I wrote 2 to the x. Is that fair? I can simplify this with log exponential properties, right? This is 2 to the x all to the 3. So this is log base 2 of 2 to the, multiply the exponents 3x. Can you follow that okay? Like, I think that this step here, where we replace the 7 with 2 to the x, first of all, you go, why do you do that? Well, because that's what's going to work for this little demonstration, but also we can because of what I wrote over here on the left, right? So you can replace anything that's equal to something else, you can replace one for the other. And then we just use exponent properties. And now what is this equal to? How can I evaluate this with the rules that we've already done? Log base 2 of 2 to the 3x equals (3x). Are people thinking that? Yes, good, right? Because the base is 2 and then the argument has a base of 2. So it's just equal to the exponent. Okay? But what is x? X is log base 2 of 7. So I can replace x with log base 2 of 7. You might not see it yet, but this is huge. Something huge just happened here. Okay, so look carefully. We started with log base 2 of 7 cubed. And then through this little demonstration, we showed that it's equal to taking the exponent of 3 out front and multiplying the log by that. This is really, really useful. One of the most useful properties, for us at least, of logarithms. That when I have an exponent on something, and they don't even have to have the same base or anything like that. Like it was log base 2 of 7 cubed is equal to 3 times log base 2 of 7 to the 1. If you are like already, you're thinking, oh my gosh, it's Monday morning, we've already done all of this, this is crazy. If you're thinking that, that's fine, but you don't need to know that where it all came from, but you need to know that property. Any questions so far? Those are all the properties that we're adding in today. Now we're going to start using them. It says evaluate each of the following using properties of logarithms. Log base 5 of 10 plus log base 5 of 12.5. Okay, ready to go? So, first thing that's interesting to see is that log base 5 of 10 is not a nice value. Log base 5 of 12.5, also some kind of nasty decimal. And if you're already starting to get logs, you would have kind of already seen that. But what property can I use? I can use one of the ones that we just did in reverse. So I'm adding logarithms with the same base. Then it's the logarithm of that same base of the product of their arguments. Ten times 12.5 is 125. 125 is 5 cubed. So that's equal to 3. 3 exactly. That surprises me. Considering that when I evaluated those logs individually, they gave like a nasty decimal. But then you do this little trickery and you get an exact answer. Nice. Everybody okay to keep going? Okay, so we can do the same thing with B. I'm subtracting logs with the same base. So we can divide their arguments. (54) divided by 2 gives us 27. 27 is 3 cubed, which equals 3. So all those demonstrations that we did on the last page, that's what it boils down to. That's kind of, generally speaking, often more so how we're going to use it. And that's pretty straightforward, right? Doing this. Question like this on a test, obviously you'd have to be doing exact value. And you'd have to show some steps. It'll say using log properties, like this question says, which means you have to show it, not just punch it into your calculator. Everybody okay? Got that down? Ready to move on? Okay. We're going to do this one two ways. Some of you are going to like one of the ways better. Some of you are going to like the other way better. And then some of you might be like, you're really doing the same thing. I don't see hardly any difference between the two ways that you're doing it. And you're all kind of right. Like everybody's going to have their preference. And the difference between the two ways we're going to do it will be subtle. But again, it is to demonstrate how interesting with logs that you can just follow slightly different paths. It's always obviously going to get you to the same answer. But, you know, some people may want to use one law more and other people might want to use another law more or be comfortable with working with the exponents in different ways. Or fractions. Sometimes it's about avoiding using fractions or something like that. Okay, so here's method one. I'm going to rewrite. First, we're almost always going to do this. If you have something given in radical form, you're going to rewrite it as an exponent, right? So this is equal to log base 2 of 8 to the 1/3. Cube root of 8 means 8 to the 1/3. We're okay with that? So I'm going to use that awesome, powerful property where when I have a power in the argument of the log, that allows me to take the exponent of that power out front. So 1/3 times log base 2 of 8. And now I don't have to worry about the fraction at all. I can just evaluate what's left. 1/3 log base 2 of 2 cubed, which is 1/3 times 3, which is 1. Or some of you might say, why wouldn't you just take the cube root of 8? Because it's obviously 2. That's something we can do. That's something that you're required to know from grade 11. And then it's log base 2 of 2, which is 1. That was one of the properties. Like, it's not that this is necessarily the most efficient way of doing it, but it gets us using the properties and getting used to the rules and seeing how you can solve these in different ways. Okay, what about if we do it like this? Log, again, I have to start by rewriting, as an exponent. 2, getting ahead of myself here, cubed to the 1/3. So I'm leaving the exponent out at this time. Now I use the property of exponents, power of a power. You multiply the exponents. You know what I mean? So this becomes log base 2 of 2 to the 3 times 1/3. Log base 2 of 2. 3 times a third is 1. So again, it's 1. So I ended up multiplying 1/3 by 3 in both cases. Like, again, some of you might say, wow, it's basically the same thing. I don't really have a preference. But some of you are going to use this a lot, where you're bringing the exponent out front. And you're going to see that as more simple, because then it's just out of the way. And I can do the rest of the question and worry about it at the end, kind of thing. And it really is up to each individual. And often I talk about efficiencies, but that's not about being efficient. That's about showing our steps, getting used to using the properties that we're exploring right now, and practicing using them. I mean, you could just punch all of these into your calculator, but that's not going to accomplish anything for us. It's not going to help us learn anything, right? Okay, again, I'm going to do this one in 2 different ways. What's 4 cubed? 4 times 4 times 4, 64? What's 2 times 64? Good, 128. 128 is which power of 2? If you were solving this in grade 11, you'd be using your calculator to check 2 to the 5, 2 to the 6, 2 to the 7. So that's equal to 7. Or I could have split this up because I'm multiplying. I have a product in the argument. I could split this up to log base 2 of 2 plus log base 2 of 4 cubed. And maybe instead of making 4 cubed 64, I do this. Log base 2 of 2 plus log base 2 of 2 squared, all cubed. Right? That would have been like a grade 11 technique. So again, power of a power, I multiply the exponents. Log base 2 of 2 equals 1. Log base 2 of 2 to the 6 equals 6. 1 plus 6 is 7. Like, I don't know. Do you think those are really all that different, or is it basically the same? It gets to be up to you. In the left one, I could have instead of doing 2 times 64 is 128, I could have done 64 is 2 to the 6. 2 times 2 to the 6, again, that's multiplying powers of the same base. 2 to the 1 times 2 to the 6 is 2 to the 7. Like I could have gone that route. If the numbers are too big, I happen to know that 2 times 64 is 128, and 128 is 2 to the 7. So that worked out for me. But if the numbers were bigger and I didn't know the powers, then I wouldn't have done it that way. So it is useful to have like some versatility to do it in slightly different ways and be confident with all the different rules and properties, right? Or I could have even not got the 64. I could have written 4 to the third as 2 squared to the third from the very beginning, right? And it would have been kind of, that would just be a mixture of both these methods that we used. What in the world is this one saying? And this is what goes through your head when this one comes up on the test. And you're like, oh my gosh, I don't even understand what that's asking. Now, we usually do a no calculator quiz, and that's where this one would probably be. So you wouldn't be able to just punch it into your calculator. If you're good at using your calculator and you don't remember this property, when the test comes around, you could just use your calculator. I don't know what a no calculator quiz would look like when students are writing at home, so it would be hard to, use the honor system, I guess. So, but normally every year we get things like this. Oh, this has got to be 3. Because 15 divided by 5 is 3, I guess. I don't know why this question is saying division, but that's one of the things that we get. We get a lot of people say the answer is 5 for some reason. There's 2 5s in there, so maybe that's the answer. But this is that one that is wonky, and it was hard when we were even exploring it, but the answer is just 15. So you just remember the 5s cancel each other because the exponent has a base of 5, the log has a base of 5. Those are opposites, they're gone, and the result is 15. So that one, that's a property we just don't use that much, but it does usually find its way onto a test, 1 question, 1 mark. And you either recognize it and remember, oh, that's that tricky one, right, that people fall for. It's just 15, or you punch it into your calculator, I suppose, if you have access to that. Questions? All right. One more working with logs like this, and then we're going to solve some equations, and then we will be done. So, again, we started off this morning having this conversation about, like, well, when are you allowed to rewrite in exponential form and when are you not? And this one says convert to exponential form. It also has an x in it, so it makes sense to convert to exponential form. But the reason why this one would be hard to evaluate as a log if I didn't have this part, if it just said evaluate without rewriting, what makes this one hard is that the base is bigger than the argument, the base of the argument. That makes this one very tricky to solve as a logarithm. Okay? But it would be an interesting challenge for you to try solving one of these without converting into an exponential form. But we're supposed to convert this one to an exponential form, so let's do it. 25 is the base stays the same. 25, that's x is my exponent to the x equals the square root of 5 all cubed. So what do we want to do? We want to rewrite that square root as in exponential form. Now I can see that I've got 2 powers. And I can rewrite 25 as 5 squared. So 5 squared to the x equals, and I'm going to simplify my exponents on this side by multiplying 5 to the 3 over 2. Some people are going to struggle with the fraction math probably a little bit in these kinds of questions. So 5 to the 2x equals 3 over, equals 5 to the 3 over 2. Again, I'm getting ahead of myself here. Therefore, 2x equals 3 over 2. Divide both sides by 2, and x is 3 over 4. Be aware that when the base is bigger, it makes it more complex. It makes it harder to do. But that's very familiar, doing it that way, rewriting in exponential form, because it's not, I mean, there's a bit of fraction math, but otherwise it's, grade 11 kind of question. Everybody okay with this? All right. Last one, we're going to solve some equations. We're starting to see the power of logarithms. Solve each of the following by taking the log of both sides. So this is another skill, another technique that we should now be aware of, and we're going to use it sometimes. And when it comes to the test, you're going to have to solve a bunch of exponential equations, and exactly how you do it will end up being up to you. I could solve these ones. I think all 4 of these that we're going to do, yep. I could solve all 4 of them by rewriting in exponential form. They're going to look similar. Okay, so you could rewrite this as 4x equals log base 10 of 1,000. That's rewriting in exponential form. That's not what we're doing. We're doing something different. And sometimes this is what you're going to do, and other times you might want to rewrite in logarithmic form or exponential form or whatever. But sometimes we want to take the log of both sides, just like you would take the square root of both sides, or just like you would divide by 2 on both sides. The trick to this one is, when you take the log, you get to decide what base to take the log in. Like, it's up to you to choose the base. So back in the day, when calculators didn't have this fancy button where you can enter your own base, they all only had the plain log button. You would always choose log base 10. So that's what we're going to do. Okay? But these days, there may be situations where you would choose a different base and not 10. Okay? So that means I do log base 10 of 10 to the 4x equals log base 10 of 1,000. So that's what it looks like to take the log of both sides. And from now on, I'm not going to write the 10 in. I'm just going to write log again. That's the reason why we would often use base 10, is because then we don't have to write the base every single time. So log base 10 of 10 to the 4x, how can I simplify that? I can never tell if people just don't want to participate or if you're not seeing it. It's equal to 4x, right? Log base 10 of 10 to the something equals that something, or log base a of a to the something equals that something. So this is equal to 4x. And I'm going to rewrite 1,000 as a power of 10. because I happen to be able to do that this time. In these questions, you won't always be able to do that. So on the right side now, that's equal to 3. And I divide by 4 to get my answer. We good? That first one worked out nicely because 1,000 is a power of 10. In this case, I have something that's not a power of 10, so it's not going to work out quite as nice. Still going to take the log of both sides. I didn't write any base, so that means it's base 10. Log base 10 of 10 to the x minus 5 is equal to x minus 5. Equals log base 10 of 50. Now what do I do? Sorry? Eventually, but not yet. I want to do one more thing before that, but that's right. Good, good intuition. We're going to use our calculator for this one. X equals, I'm going to add 5 to both sides. Again, I talked about ambiguity before. If I wanted it to be log of 55, I would have to put brackets around all of that to show that it's 50 plus 5. If it's shown like this, it means log of 50. And the plus 5 is outside the argument. So be careful of that. People do make mistakes in that. So now I get out my calculator and I go log of 50, close bracket, plus 5. And it gives me 6.7. The instruction said round to 1 decimal place if necessary. So again, you would have chosen base 10 because in particular, if that's the kind of calculator you have, that's the only base you can do. So why wouldn't you choose base 10? The rest of you might choose base 10 because, well, it canceled on this side, so that made that work out nicely. And it's a little bit easier, it's less typing in your calculator. Like if you still have, like on mine, you still have that straightforward log button. It's a little bit faster to use that rather than typing in the base. You know what I mean? So if you had that fancy button, you might choose base 7 here, log base 7 of 7 to the 2x, because then those 7s are going to cancel. You're just going to get 2x. Because you can choose the base. But I'm sticking with base 10 because that's kind of the point of this lesson. So log base 10 of 7 to the 2x equals log base 10 of 2500. I'm going to use that awesome property where I can bring that exponent of 2x out front. See how often we use that? If there's one thing you take away from today, from this lesson, it's got to be that property. That's not going to get you every question answered, but it's going to be crucial for a lot of what we do. So 2x times log of 7. The reason why it's so powerful is I've got an x in the exponent. Now I don't. Now my x is down in line with everything else. I'm just multiplying by it. That's so much easier to work with. Now what do we do? And this again is part of getting used to logarithms. What is log of 7? I mean, I don't know what it is, but it's a number. Right? I could punch that into my calculator. It's some decimal. So can't I divide by that on the other side? I'll also divide by the 2. So it joins the log 7 on bottom. You could have done all that in one step, of course. Are we okay with this? Not going too fast? And then I punch it into my calculator. Log of 2500 divided by 2 log 7. I have noticed on these calculators, when you have a fraction, if you don't close the bracket, it will give you an error. So you got to close the bracket, because normally you don't have to, right? But 2.0. Punching these into your calculator will be a little bit of something you got to get used to. In the next lesson, we're going to do some very big equations, and they're harder to punch into the calculator, so just be mindful of that. That practicing with your calculator is part of what we're going to do. Okay, last question. There we go. Nothing really special about this one. I don't know. If you want to give it a shot, go for it. We're going to do the same thing. Take log both sides. And I got negative 0.3. Any questions? So we did a couple of things. We explored some properties, and we saw some of those properties in action, how we can use them to solve problems. Sometimes they make big problems into small problems kind of thing. They make something that was complicated, they kind of make it easy or easier. We learned about a couple of really important properties that, again, we were using that just come up in logarithms all the time. When we do calculus, we do this thing called logarithmic differentiation, and we take advantage of this property, and it allows us to take the derivative of something that is the point of calculus and something that you couldn't otherwise. We use logarithmic differentiation, so it's really, really useful. And then we did some solving equations by taking the log of both sides, right? So there's sort of two different things, but we're using the properties in here as well when we're solving these equations.